Hi. So, small problem I noticed when we were doing calc AB and BC is that we never really get to prove the fundamental theorem of calculus. So, which is the integral of x from a to b is equal to antiderivative fb minus antiderivative fa. So, I want to try and prove it. So, first of all, what we have to do is something called a partition of a and b. Partition of a and b. And that's essentially finding numbers x0, x1, or you can actually, for sake of simplicity, start with x1, x2, all the way to xn, such that we have a equals x1 less than x2 less than x3 less than blah blah blah, xn equals b. So essentially we're going to cut this interval into many parts that don't necessarily have to be equal, and then now we're just going to, so now we have this partition. So how are we going to use this? So we're going to use the mean value theorem considering f of x, the antiderivative of f of x. So what we're going to do here is we're going to consider each of these small intervals by themselves. So let's say we have xi, and we're looking at the interval xi to xi plus 1. And remember, both of these x's are going to be within this big interval of a to b. So the mean value theorem states that for this range, there has to be a value, let's call it z, such that big F prime z equals big F xi plus 1 minus big F xi over xi plus 1 minus xi. Remember, these are subscripts, so we can't just cancel them out. And if we multiply these, both sides, what we get is fc. Remember, since this is antiderivative and we're taking derivative, we can just simply turn it into regular fc. Am I blocking it? Equals to, we're multiplying over xi plus 1 minus xi equals big F xi plus 1 minus big F xi. So now what we can do is we can add like a cool little summation here, right? So let's do that, shall we? So what we're going to do is we're just going to, let me just erase this part, we won't need this. What you can essentially do is we're just going to add some sigma notation, I equals 0, n, and then we just add, it was fc times xi plus 1 minus xi equals sigma notation, I equals 0, f xi plus 1 minus f xi. There you go. So what are both of these? For the right side, it's really easy. It's just a telescoping series, because if we just route the first two terms, you'll see a really clear pattern. F1 minus f0. Oh wait, it starts at, I made a small mistake, didn't I? Oh yeah, I'm going to start with 0 for this one, but you get the idea. f1 minus f0 plus f2 minus f1 plus f3 minus f2 plus blah blah blah. And as you can see, everything starts, not the f0, everything starts to cancel out. Yeah, this doesn't cancel out, this stays here. And then what we'll eventually leave with is, we're going to eventually end up with, actually, for the sake of simplicity, I'll go to n minus 1. I don't want to see an n plus 1 here. We're going to end up with fn minus f0. And this is the right side. Up. And remember our definition, this is basically equal to b minus a. Because remember our definition of fn being, like the last one being b and the first one being a. Well, here we are, b minus a. So what we have here is just the left side. So I'm just going to get rid of all this since we don't need it anymore, just for the sake of saving space. This is simply just a Riemann sum, isn't it? Right? This is the x part. This is how high it is. This is just Riemann sum. And what is and as we get the number of, n's bigger and bigger, what happens to the Riemann sum? That's right. It turns into an integral, doesn't it? Right? So this is essentially just integral. So here we are. W proof, isn't it? So this is just a good attempt. I hope it makes sense. There probably might be there definitely are some small errors here and there scattered about, But overall, I think this is a pretty solid proof about the fundamental theorem of calculus, which is great. So yeah.